Hey everyone, I'm Ethan, and together with my group Dolce Codece, we're here to discuss our project on enhancing the architectural design of flight gear. Today we will explore the integration of a fully interactive hangar environment aimed at dramatically enhancing user immersion within this popular flight simulation software. Here is our member contribution. Introduction. FlightGear stands out as a premier open-source flight simulator, offering an array of aircraft and environments that mimic real-world flying conditions. Building on the existing conceptual and concrete architectures we've previously analyzed, our project introduces a significant enhancement, a hangar environment. This addition allows pilots to navigate through hangar buildings, interact with aircraft, and personalize their flying experience before taking to the skies. This innovative feature aims to bridge the gap between selecting an aircraft from a menu and experiencing the tangible process of preparing for a flight, much like a real pilot does. Our proposal is to integrate a third environment, the hangar, into the existing framework of FlightGear. This hangar environment, distinct from the active flight and airport scenes, is designed as a space where players can physically interact with aircrafts. The hangar serves as both a transitional and standalone exploration area, providing an immersive platform where players can inspect, customize, and choose their aircraft in a visually rich setting. This environment will facilitate a deeper connection with the aircraft, enabling players to appreciate the intricacies of various models and potentially fostering a community-driven initiative to enhance and expand the available aircraft models within FlightGear. In the first implementation, we introduced several new subsystems designed to integrate seamlessly with FlightGear's existing architectural framework, enhancing the simulation's capabilities without altering its core functionality. The cornerstone of this approach is the hangar interface, a sophisticated subsystem that employs the scenery and environment subsystem to create intricate, highly detailed 3D models of hangars. These models feature dynamic lighting to enhance realism and provide various interactive points, allowing users to engage directly with aircrafts. Furthermore, the hangar interface is not just about visual enhancement. It strategically positions aircraft with the hangar for optimal interaction. Whether users want to inspect an aircraft's exterior or climb into the cockpit, the interface facilitates these interactions smoothly and realistically. To complement the visual and interactive enhancement, we developed the character movement and interaction system. This subsystem introduces advanced character animation and control, enabling users to navigate the hangar in a realistic manner. Supported by a custom-built physics engine, it ensures that all movements within the hangar, from walking to interacting with objects, are smooth and true to life, enhancing the overall realism of the user experience. Another pivotal subsystem in this implementation is the transition management system. Its primary role is to manage the flow between different simulation states seamlessly. This includes transitions from the main menu into the hangar, from the hangar to the aircraft selection, and eventually into the flight simulation itself. It ensures that all user configurations and customizations are maintained throughout the simulation process, providing a cohesive and uninterrupted experience. By integrating these subsystems, implementation number 1 not only enhances the user interaction within the hangar, but also ensures that these interactions are deeply integrated with the overall flight simulation, providing a seamless transition between different phases of the game. In our second approach, we focused on modifying and extending the capabilities of existing subsystems to accommodate the new hangar features. This strategy centers on the innovative use of the flight dynamic model, which traditionally handles only the physics of flight. Our enhancement allows it also manage player movement within the hangar, a novel adaptation that integrates walking physics into a system originally designed for aircrafts. To achieve this, we explored two possibilities. One involves adding a pseudo-aircraft model that represents the player in the hangar, utilizing existing FDM mechanics to simulate walking. The second approach is more radical, and it involves adapting the FDM to support invisible models that enable navigation and interaction within the hangar without the visual representation of an aircraft. Alongside the changes to the FDM, significant updates were necessary for the scenery and environment subsystems. These updates were designed to incorporate detailed representations of hangars as environments within the existing geographic landscapes, complete with interior mappings and accurate lighting reflections to enhance them. The GUI also required adjustments. While the core interface elements remained consistent with the rest of the game, Modifications were made to accommodate the unique aspect of the hangar's environments, such as interfaces for the aircraft inspection and customization before flight. These adjustments ensure that the hangar environment feels like a natural extension of the overall flight gear experience rather than a disjointed addition. This approach, while conservative in its preservation of high-level architecture, demands meticulous attention in detail in modifying existing subsystems. It challenges us to reimagine the capabilities of these subsystems, extending their functionalities to encompass new, groundbreaking features that enrich the user experience without compromising the simulation's integrity.
Awesome. So I'm gonna take it over from Ethan. So right now we're just gonna talk about the risk and effects. So when we're talking about the risk and effects, we usually gonna focus on the security, testability, performance, evolvability, maintainability, scalability, and availability. So for example, when we're talking about the security, we're talking about the minimal risks outside of those that are already present. So we're trying to make sure that it's as secure as possible. Testability, we're making sure that the implementation follows similar and easier implement testing models. And for the performance, we have to make sure that the performance is not affected that much when we're adding any new thing into the system. And same thing for scalability and availability. It's all about making sure that the user experience is as good as possible and that the user will not have any problem using the website for the flight gear. So for the SAAM analysis, for our users, we prioritize the NFRs such as availability, ensuring the software accessible is accessible when needed, usability for an intuitive and efficient user experience, performance to maintain high speed and efficiency, and reliability to ensure consistent operation without failure. So for the developer side, we focused on scalability to handle growing amount of work gracefully, testability allowing for easy verification of the system's operation, and maintainability for straightforward updates and bug fixes. So we consider two potential implementation methods, which I will go through them with you guys. Alright, so let's go through the first use case. So in this scenario, we're looking at a user experience that is both interactive and immersive. So the user enters a 3D hangar environment where they have the ability to select and configure their aircraft. And it's not just about clicking the options, it's about interacting with the virtual environment in a way that feels real and engaging. And that actually make it seamlessly transition the user to the flight simulator, which isn't just to cut a new screen, it's a carefully managed transition that maintains an immersive experience. Alrighty, so for use case 2, this process begins with the user starting at the hangar, which triggers a series of events in the system's architecture. First, we see the initialization of the hangar environment, involving several subsystems such as RTI Manager and the scenery and environment components. They work together to create an immersive and dynamic virtual space. And the important aspect comes into play where the FDM is crucial as it's the models the player's movement within the hangar, ensuring that the virtual experience is as realistic and responsive as possible to the user input. Mainly, the lesson that we learned this time was the importance of multiple elements on the effectiveness of an implementation, and that really did was an interesting part of our research and our report this time. And how stakeholders and NFR lead to implementation one being more effective solution. And that was basically mainly because of how easier it was implemented that rather than implementation 2. Awesome. So let's jump into the conclusion. So the four main conclusions we've got was the enhancement benefits, successful integration, technical achievements, and the lessons learned. So for the enhancement benefits, it was the hangar enhanced significant the enhancement of the hangar, and then the successful integration was the implementation one and how we found out it's better than implementation two, and technical achievement and that how it demonstrates the robust system architecture by successfully integrating complex new features. And the lesson learned, I just went through them.